There are very few series whose exact value we can compute directly from the definition. It's pretty much just geometric series and a few telescopic series. Yes, we can tell whether they are convergent or divergent using the convergence test, but we don't know what they add up to. That's about to change. Now that we have Taylor series, with a little bit of creativity, we can compute the exact value of many more series. I'm going to illustrate how to do this with two examples in this video. In this first example, I want to compute this sum, the sum from n equals 1 to infinity of n over 2 to the n. It is easy to see that it is convergent. For example, use the ratio test, but I want more than that. I want to know what the exact value is. What I'll do first is I'm going to interpret this as the value of a power series. What I want is the value of this sum from n equals 1 to infinity of nx to the n when x equals 1/2. It may seem that I'm making the problem harder rather than easier, because instead of a fixed number now I have a variable, but I have more tools when I look at power series. And the first thing I notice is that this reminds me of another power series whose value I know. This is almost, not quite, but almost, the geometric sum. We know the value of the geometric series. Except I have an additional n in there. I have this additional n. But now, if I have x to the n and I want an extra n multiplying, one way to accomplish this is to simply take the derivative. Because I know the derivative of x to the n with respect to x will be n times x to the n minus 1. So let me write down what happens when I take this derivative. Since this is a power series, we know we can take the derivative term by term. The derivative of x to the n is n times x to the n minus 1. Let's see where it starts. Here I don't need to worry about the term when n equals 0. The term when n equals 0 is a constant, which I can separate, and the derivative is 0, and then I only need to worry about the derivative of the rest. If I were to include n equals 0 here, nothing bad would happen, because the coefficient is 0. There. So I know how to add up this sum, I'll take the derivative, and then I get this sum, and this sum is almost what I need. The only difference is that I need to multiply times an extra x, but I know how to do that. So great, this is going to work. Now I have a plan. So let's execute this. We know the sum of the geometric series is 1 over 1 minus x, whenever the absolute value of x is less than 1, but that's okay. The value where I will evaluate is in the correct domain. And then we know that the derivative of this is 1 over 1 minus x squared times minus 1, that cancels. Perfect. So now, the sum I'm actually looking for from n equals 1 to infinity of n times x to the n will be the previous one times x. So x over 1 minus x squared. And that's it. To conclude, I'm going to evaluate this at x equals 1/2. And I get that the sum I was looking for is equal to this expression when x equals 1/2, which is 2. And that is the final answer. For my second example, I want to compute the sum from n equals 0 to infinity of 2 to the n over n plus 2 and n factorial. Like before, I'll begin by interpreting this as a power series. And now, I need to look for a power series whose value I already know that is close enough to this, and then manipulate it until I get this one. In this case, this reminds me of the power series for the exponential. If I didn't have the n plus 2, I would know the sum is e to the x. All I have left to do is throw that extra n plus 2 in the denominator. Well, when I have a power, the way to throw something like that in the denominator is with integration. Specifically, if I have x to the n plus 1 and I integrate it, I'm going to get x to the n plus 2 over n plus 2. And that's how I'm going to throw an extra n plus 2 at the bottom, which is the only piece that I am missing. Now, the n factorial, I'm going to treat it as a constant. And the fact that I have a sum, well, I'm going to commute that with the integral. And we know we can do that because we are dealing with a power series. And of course, don't forget the integration constant. So that's it. What I need to do is take this sum, then integrate it, and I will get the extra n plus 2 at the bottom. Now this sum is not exactly the one I have here, but it's very close. If I know the value of this sum is e to the x, what will the value of this sum be? Well, it's the same sum times an extra x. So I can reinterpret this as the integral of x times e to the x. There. And I think I have a plan now. So I need to take the function x e to the x, compute an antiderivative, adjust the integration constant, and then I will have the value of this sum. And then to go from here to here, all I have to do is divide by x squared. And after that, I will evaluate at x equals 2. Okay, so let's do those steps. First is the integration. Probably the best way to integrate this is with integration by parts. So if you need to do intermediate steps, go ahead and do them. And an antiderivative is going to be equal to x minus 1 times e to the x. So this is equal to this series plus an integration constant. I need to know what the constant is. The best way to do that is to evaluate at an easy point, and the easy point is in this case 0. When x equals 0, the left-hand side would be minus 1 times 1. And on the right-hand side, I have this series. When x equals 0, that's 0 plus c. So the constant is minus 1. So that means that this sum is going to be equal to this function minus c, which could be 1. And the rest is algebra. I first divide by x squared, and finally I need to evaluate when x equals 2. Two minus 1 is 1 times e squared plus 1 over 2 squared, that is 4. And that is the final answer. Cool, eh? These calculations are fun. If you want to try your hand at them, here are a few exercises that you can solve with the same techniques.